Welcome back to the bench. Today I'm going to look at Schottky diodes. Schottky diodes are a special type of diode. Normal diodes have an N and P type semiconductor junction. Schottky diodes have a semiconductor to metal type junction, and that gives it some interesting characteristics. So I went through my parts drawer of diodes and pulled out some Schottky diodes and a few regular diodes to compare it with. And I laid them out here. This is the part number. Under that is the voltage and current rating. So I'm going to perform some tests on these diodes and see what the results are. Before I get on with the tests, I want to talk about the advantages and disadvantages of the Schottky diode. First, the advantages. First advantage is a low forward voltage drop. If you take an ordinary PN junction silicon diode, apply a forward bias to it, it will not start conducting until you reach around 700 millivolts, give or take, depending on the current. And that could be a source of power loss. For example, let's say you have 3 amps current passing through the diode and it has the 700 millivolt drop across it. Well, the diode's going to dissipate a little over 2 watts. So, that's a significant loss of power right there. A Schottky diode, on the other hand, has a lower forward voltage drop. It'll be around 300 or 400 millivolts, give or take, again depending on the current and the type of diode. So you will save about 50% of losses right there. So that's an important advantage. Next advantage is fast switching. Because of the design of the diode, it can switch at a higher frequency than ordinary silicon diodes. Ordinary diodes have a reverse recovery mechanism where Schottky diodes don't really have that issue. So they can switch fast. You probably heard of fast switching diodes or fast recovery diodes. Schottky diodes are even faster than those. Now on to the disadvantages. One disadvantage is they're relatively more expensive. Diodes are not that expensive. They're not a real big deal to the weekend hobbyist. But if you're designing a product and using a Schottky diode is going to cost a few more pennies more than an ordinary diode. You might be able to purchase in quantity diodes at, like 5 cents a piece. But a Schottky diode might set you back 15 cents a piece in quantity. And if you're making several million copies of a product, that adds up in the costs. So yeah, there is some expense to consider. Another issue is the reverse leakage. Schottky diodes tend to leak a little bit of current through them, and it's usually not an issue in most cases, but there are situations where it can be a problem. And in some cases, as the diode heats up, there could be a reverse conduction thermal runaway issue. As it heats up, it conducts a little more, and that causes more current to flow, and it heats up even more, and you can see it just becomes a thermal runaway issue. So these are just some basic advantages and disadvantages. There's a little more detail to talk about this stuff when I actually run the tests. Not everything is so cut and dry in electronics, and we'll take a look at that here. Alright, let's move on with the tests. Okay, I'm going to start with a switching speed test at 1 megahertz. What I have is a microcontroller, and I programmed its pulse width modulated output to give me a 1 megahertz signal or square wave on the output, and we'll use that to test the speed of these various diodes and see how they perform. One thing I found that's very important is to set up your scope properly. You have to use the probes in 10x mode. and I have to keep these wires short. First I tried using alligator clips, and the length of those leads had extra inductance in it, and it was causing a lot of ringing in the on the oscilloscope screen. So I just using this little lead here, and I'll just have to hand hold the diode and get a reading off the scope. Okay, I'll point the camera at the scope while I'm doing this and announce what device I'm testing. Here's a schematic of my test setup. I have my 1 megahertz signal source here. Passes through a 220 ohm resistor into the diode under test, and the scope leads will connect here. This is the ground side. You have to use both grounds because if you leave one lead off, you'll get a lot of extra inductance and you'll get ringing. One channel will connect across the diode under test, the other across the signal source, so you can see that original source as a reference. And by the way, this is the schematic symbol of a Schottky diode. Okay, so I have the waveform up on the screen. Those microcontrollers can give you a nice waveform. It does have a little bit of overshoot. See, I have the channels on top of one another, but the direct output of the microcontroller does have a little bit of overshoot. That's not my scope probe. It is actually that way because when I move the lead to the same place, I don't get that anymore. So channel 1, the yellow channel, is going to be the actual device under test. You might see the blue channel or the microcontroller output drop a little bit. That's just because we're loading it down. So first I'll start with a 1N5404. That's just an ordinary 3 amp rectifier diode. And let's take a look at what happens here. Okay, forward bias. Okay, so what's happening here is, when the output turns on, the diode turns on, and you can see this is about 0.7 volts because this is our baseline and we're a volt per division. But when the output of the microcontroller goes low, the diode doesn't change. It stays on. It's not fast enough. So you can see the result there. These diodes are not very fast. They're just meant for like around 60 hertz. They can do a little faster than that. Next, we'll take a look at a fast recovery diode. It's an NP junction fast recovery diode. It's not a Schottky. It's FR306 if you're wondering. So let's see what happens when we try that. Well, it's still not fast enough. You can see there is a little bit. Let me turn this up. You can see there is a little bit of change in the voltage level, but it's not turning all the way off. So this particular diode is not very fast, at least for 1 megahertz. Okay, now I'll try a Schottky diode. This is an SB330. It's a 30 volt 3 amp diode. Okay, and you can see the forward voltage drop is quite a bit lower, and it's hard to tell. So let me turn the channel up. So we're at 200 volts per division. So it's a little over 200 millivolts when it's turned on, and you can see it is dropping down. So yeah, this is kind of weak for such a high frequency, but you do see it is switching a lot faster. Now, just for comparison, let's turn that back down. I'm going to try a ordinary silicon diode, one of these small signal type diodes, switching diodes they call them. This should be pretty fast. And yeah, look at that. You can clearly see it is switching off. Let me turn that up. So we're around 600, 700 millivolts, and it does turn off pretty quickly. A slight little curve here, a little bit of delay. You can see a little turn on spike there. It's not instantaneous. And I'll try, did I say it's a 1N914? If I didn't mention that before. Now I'll try a Schottky diode. It's a signal diode as well. And a kitty came in. Though its voltage is definitely higher. It's like 1 volt. It's probably not meant for the current I'm putting through it. 20 some milliamps, but let's see here. Turn that up. It's switching about the same. It's maybe a little better. It definitely turns on better. There's not a huge turn on spike. So you can see there the comparison of those two types of diodes. Now I'll show you another interesting aspect of the diodes here. I'm going to connect them in reverse bias. So they're not actually going to turn on, but you still will see an effect. See what's happening there? That is caused by capacitance. This is the 1N5404 again. And there is some capacitance. Whenever you have differential in voltage at a very close distance, you're going to have capacitance effects across that. So that was the 1N5404. Let's try the fast recovery diode. And about the same. And now the Schottky diode, the SB330 again. See that? It has a lot more junction capacitance. Now let me try a 10 amp Schottky diode. This is the TO220 case. See what its capacitance looks like. Yeah, you're seeing the charge and discharge curve of the capacitance. And I think it has a little bit more capacitance. I mean, it's a beefier 10 amp diode, so see what's going on there. So there is more capacitance in the Schottky diodes that I'm seeing here. So that can be detrimental depending on your design, especially in a very high frequency switching. Okay, that was interesting. Let's move on to the forward voltage drop test. Okay, so now I'll use my power supply in current limit mode, and I'll test at different current intervals of the voltage drop across the diode. So at 100 milliamps across the 1N5404, getting 0.72 volts. And I'll go through several different current levels, and I'll test all of these diodes. I'm not going to sit here and do it all on camera, but I'll log in the data and come back with the results. Okay, here's the results for the 1N5404 ordinary silicon diode. It started at 720 millivolts forward voltage drop at 100 milliamps. Then I went to 200, 500, 1 amp, 2 amp, and 3. You can see it started to rise, but then it started to drop again. The reason for that is it gets really warm at higher currents, and at higher currents the forward voltage drop actually starts to decrease again because of the heat. Okay, so now I switched over to the SB330, and we'll see how that performs. Only 293 millivolts. So you can see how much lower the forward voltage drop is. So I'll log that in and continue testing. And here is the results of the SB330. notice the much lower voltage drop of the forward voltage. I did notice it was a lot more temperature sensitive. I had to let it stabilize. As it heats up, the forward voltage did drop. But you can see across the voltage range, it did change quite a bit. But at its maximum level, it's still quite a bit less than the silicon diode. Well, you might say, well, this is a 400 volt diode versus a 30 volt Schottky diode. Is that a fair test? Well, if I had a 50 volt version of this, I would get similar results. I just don't have a 50 volt version on hand, so I had to use this diode. Okay, so anyway, I'm going to continue testing all these other diodes and come back with results. And here is the forward voltage drop test results. As you can see here, all the Schottky diodes had a lower forward voltage drop than the standard silicon diode by a pretty significant amount. Now, of all these Schottky diodes, the STPS 5L60 60 volt 5 amp diode had the lowest forward voltage drop of all of them. In fact, you see here's a 100 volt 10 amp Schottky diode. At 3 amps, it was 520 millivolts, whereas the STPS 5L60 was only 372, and it's better than the other ones. Of course, this one's only a 1 amp diode, so I didn't test it beyond 1 amp. And yes, this little ST Microelectronics diode, the STPS 5L60, is my favorite diode. It has a very low forward voltage drop, so it's going to provide the lowest losses of all these others if you're using it as a blocking diode, for example, for like a solar panel. One thing you notice about Schottky diodes is their blocking voltage rating is pretty low. I mean, you have 20 volts, 30, 60, 45, 100. And there's a reason for that. To get this very low figure of the forward voltage drop, you have to select a blocking voltage that's pretty low. And you have to be careful when you're designing your circuit that, you know, the maximum voltage that the diode blocks doesn't exceed its rating, or you could possibly damage it. Now, in recent years, they've come up with higher voltage Schottky diodes. I guess they're based on silicon carbide, and they can operate up above 1,000 volts. However, their forward voltage drop is not as good as these lower voltage ones, but they still might be better than a standard silicon diode. In fact, they are pretty close actually. It's just mainly the fast switching speed benefits you get from those. So now I'm doing a reverse bias leak test to see how much current these leak. First, we'll start with the 1N5404, and I'm passing the current through a green LED. Apologies, I do have to hand hold the camera, but nothing, no leakage at all. Okay, now I have the 1N5817, and you can see the LED is glowing, and it's passing about 2.6 microamps. Not a lot, but yeah, there is some reverse conduction. The voltage is 12.61 minus the LED drop, around 10 volts or so across the diode. Okay, we'll try one more. This is the STPS 5L60, and you can see the LED is glowing brighter because it's passing about 12 microamps. Now let's see what happens. I have this resistor here. It has 5 volts across it, and it's 25 ohms, so we get exactly 1 watt dissipation. and you can still touch it. It's not real hot. So I'm going to put this diode on there and watch how the current increases. Okay, so I let it go a minute and it's more than tripled its leakage current just from the heat. And it's still nothing serious, 40 microamps. But in some situations where the diode can get really hot, the reverse conduction can become significant and thermally run away, actually. But the diode would have to get really hot to do that. It'd be a poor thermal design for that to happen. Schottky diodes are commonly used in power supplies and switch mode regulators. They utilize the energy in the collapsing magnetic field of the coil, and they're often called flyback, freewheeling, or even efficiency diode. The designer of the circuit has to weigh all the properties, the forward voltage drop, the switching speed, and the extra capacitance to see if it's the best type of diode to use in their circuit. In this example here, this is a little switch mode regulator. It has an SS54 flyback diode right here, and it turns out to be a Schottky diode. So there you have it. A little delve into Schottky diodes. Appreciate everybody watching, and we'll see you next time.